So here we're going to talk about Mohr Circle, which is really just a graphical way that we could do these stress and strain transformations. So again, we start with our state of stress, sigma x, sigma y, and a tau. Okay, and what we're going to actually do is we're going to set up coordinate, and here's a picture of Mohr Circle that I'll be referring to. So the first thing we do is we set up our coordinates where the normal stress is positive to the right and tau is positive down. Okay, so I've got tau here and the normal stress sigma horizontally. Okay, then I find the center of the circle, which is basically at that average stress. So sigma x plus sigma y divided by 2. That'll give me the center of the circle, sigma average. Then I go ahead and determine the radius, which is given by this equation right here. Okay, so then I know the radius of the circle. I can actually draw my circle now at the center with the radius given at this equation here. And again, this comes from, if you go back into our transformation equations, this actually comes from the principal strains. Essentially, it's this plus or minus. It's the center plus or minus the radius that gives us our principal strains. And that'll make sense here in just a second. Okay. So before I move forward, I'm going to go ahead and locate basically the state of stress on the circle. So basically I find my sigma x and my tau. So sigma x and then some distance tau here, and I'm located at point A. That is my basic start location. Be aware that over here will be sigma y, 180 degrees around the circle. So if I draw a straight line across AC up here, this would be where sigma y would be. Okay. Now, the principal stresses are basically at locations B and D, which is where I cross this, where I'm at my maximum sigmas, right? And my tau is 0. So hopefully you can see now where this equation kind of comes from based on our principal stress equation we did when we developed the transformations. Okay, and my maximum shear is either F or E, here or here. That's where my maximum shear is, again, at that sigma average that we have here, F and E. Okay, so it's just a graphical way of seeing where the principal and the maximum plane shear stresses are. Okay, now if you go from your state of stress, you can determine the angle. Okay, basically I go 2 theta around this angle, similar to just a regular theta in the actual element that I'm looking at. So I can determine the angle that I move. Say if I'm going from my state of stress to the principal stresses, I can find that angle. Okay, that will give me the orientation, knowing that that angle is 2 pi on the circle, not 2 pi, excuse me, 2 theta on the circle, and just theta on my element. So that's how I can set up Mohr Circle to kind of graphically figure out where these points are. And I can do something similar for strain. Again, just substituting epsilon in for theta. By theta I mean sigma, excuse me. Stress versus strain. And then remember, tau actually goes to gamma over 2. But otherwise I set things up exactly the same way. I can find the center, the radius, everything looks the same. Okay, and do it for strain as well as stress, just by, again, remembering that my shear is gamma over 2 rather than just tau. One other thing I want to talk about here are strain gauges. And what strain gauges are is a little piece of wire, basically, that you cement onto some material that's under a strain. And as that thing is strained, the resistance in that wire changes a little bit. Okay, and if we measure the resistance, then we can then measure the strain occurring on that strain gauge. Now, specifically, we're going to talk about a rosette, which is actually a cluster of 3 strain gauges on a single plane, and we use this to determine the state of plane strain, essentially. Okay, so we set up these strain gauges at known angles from one another. Okay, and then using the values of those strains, I can actually develop the state of strain that I have at that point. And I do this by basically solving the strain transformation equations simultaneously. So if you go back into the development for strain, okay, we can write each strain, okay, in terms of its x, y, and gamma values. Okay, and we do that knowing the specific angles at which they're located, theta A, theta B, and theta C, and basically using the readings epsilon A, epsilon B, and epsilon C, I can find epsilon X, epsilon Y, and gamma XY. It's basically 3 equations, 3 unknowns that I can solve for here. Now, if I set this up in very, very common orientations, basically a 45-degree rosette, well, the strain in A is the strain in X, the strain in C is the strain in Y direction, and then I can find gamma from this equation here. And essentially that's just solving these 3 equations, plugging in 45-degree angles for where things are necessary. Okay. Similarly, a 60-degree, where the gauges are 60 degrees apart, I can set it up so the strain in the A is the strain in the X, and then again solving these 3 equations, 3 unknowns, knowing every angle is 60 degrees, I can determine epsilon Y as well as the shear strain. Okay, so that's how we use strain gauges to determine that state of strain, and then using Hooke's law we can actually get to the state of stress, which is oftentimes more useful to us.